Welcome back to the computer lecture series by Get Billy. Uh, Learning computer with seeing the natural sights of Indian village. In this lecture, we will talk about the types of processor. So first, we see the CISC processor, CISC processors. One of the earlier goals of central processing unit designers was to provide more and more instruction in the instruction set of a central processing unit to ensure that the central processing unit supports more functions directly. This makes it easier to translate high-level language program to machine language and ensures that the machine language programs run more effectively. Of course, every additional instruction in the instruction set of a central processing unit requires additional hardware circuitry to handle that instruction, adding more complexity to the CPU hardware circuitry. Another goal of CPU designer was to optimize the usage of expensive memory. To achieve this goal, designers tried to pack more instructions in memory by introducing the concept of variable length instruction, such as half word, one and a half word, etc. For example, an operand in an immediate instruction needs fewer bits, and hence a CPU designer can design it as a half word instruction. Additionally, designers originally designed the central processing unit to support a variety of addressing modes. CPUs with large instruction set, variable length instruction, and a variety of addressing modes are called CPU based on CISC, complex instruction set computer architecture, CISC architecture, and CISC is a abbreviation of complex instruction set computer. Since complex instruction set computer processor possess so many processing features, they make the job of machine language programmers easier. However, they are complex and expensive to produce. Most modern personal computers use CISC processor. Now the next topic is RISC processors. In 1980s, some CPU designer, that is central processing unit designer, realized that many instructions supported by CISC-based central processing unit are rarely used. Hence, they came up with the idea of greatly reducing design complexity of a CPU by implementing in hardware circuitry only bare minimum basic set of instruction and some of the more frequently used instructions. The instruction set of the CPU need not support other complex instructions because a computer can implement them in software by using the basic sets of instructions. While working on simpler CPU design, the designers also came up with the idea of making all instructions of uniform length so that the coding and execution of all instructions becomes simple and fast. Next, to speed up computation and to reduce the complexity of handling a number of addressing modes, they design all instructions in such a way that they retrieve operands stored in register in central processing unit rather than from memory. These design ideas resulted in producing faster and less expensive processor CPU processors, central processing unit with a small instruction set, fixed length instruction, and reduced reference to memory to retrieve operands are called CPU based on RISC reduced instruction set computer architecture. Since RISC reduced instruction set computer architecture processors have a small instruction set, they place extra demand on programmers who must consider how to implement complex computation by combining simple instructions. However, RISC processors are faster for most applications, less complex and less expensive to produce than CISC processor because of simpler design. Popular RISC processors used in workstations are Power used in IBM workstation, Spark used in Sun workstation, and RISC used in HP workstations. Supports of RISC technology claim that increased processing speed and lower cost of RISC processors easily offset the limitation of a reduced instruction set. However, critics of RISC technology are of opinion that a RISC processor has to process more of these simple programmed instructions to complete a task, placing additional burden on system software. There seems to be no clear answer as to which technology is better. The answer may be that each technology lends itself best to certain application, and so both technologies will coexist. Mm. Now we know about the EPIC processor, that is explicitly parallel instruction computing, EPIC, EPIC. E for explicitly, P for parallel, I for instruction, and C for computing. Explicitly parallel instruction computing. This technology breaks through the sequential nature of conventional processor architectures by allowing the software to communicate explicitly to the processor when operations can be done in parallel. For this, it uses tighter coupling between the compiler and the processor. It enables the compiler to extract maximum parallelism in the original code and explicitly describe it to the processor. Now, EPIC processors use the following three key techniques. First, explicit parallelism. This technology breaks through the sequential nature of today's conventional processor architectures by allowing the software to communicate explicitly to the processor when the system can perform an operation in parallel. For this, it uses tighter coupling between compiler processor compiler processor. It enables the compiler to extract maximum parallelism in original code and explicitly describe it to the processor. At its compile time, the compiler detects which of the instruction can the system execute in parallel. It then records them and groups them in such a way that the system can execute instruction belonging to the separate groups in parallel. At runtime, the processor exploits this explicit parallelism information provided by the compiler to execute the instruction faster. Second, predictions. Prediction technique improves performance by reducing the number of branches and branch mispredicts. Once again, the system first takes the help of compiler to reorder the instruction to reduce the number of branches as much as possible at compile time. Conventional processor use branch prediction techniques in which the processor predicts which way a branch will fork and speculatively execute the instruction along the predicted path. At the time of execution of branch instruction, if the system finds the prediction to be correct, the processor gains performance improvement because instructions lying in the path to be executed now have already been executed and the processor can use their results directly. However, if the system finds the prediction to be wrong, it discards the result of the execution of the predicted path and takes up the instruction of the correct path for execution. However, EPIC technologies uses branch prediction instead of branch prediction. In these techniques, instead of predicting and executing one of the paths of a branch, the processor executes instruction of all the path of the branch exploiting as much parallelism as possible. Now when the processor discovers the actual branch outcome, it retains the valid results and discards other results. Thus, branch prediction effectively removes the negative effect of branch prediction techniques in case of branch mispredict. The third one is speculations. These techniques, that is speculation techniques, improves performance by reducing the effect of memory to processor speed mismatch. Memory access speed is much slower than processor speed. Speculative data loading techniques take care of this by loading a piece of data and keeping it ready before the processor actually requires it. It not only allows the processors to load a piece of data from memory before a program actually needs it, but it also postpones the reporting of exception if the loaded data is illegal. We can also implement the speculation techniques by taking help of compiler. For this, the compiler analyzes a program at compile time looking for an instruction that will need data from memory. It inserts a speculative load instruction in the instruction stream of the program well ahead of the instruction that need data from memory. It also inserts a matching speculative check instruction immediately before the instruction that need data from memory. It now records the surrounding instructions so that the processor can dispatch them in parallel. Now, when the processor encounters a speculative load instruction at runtime, it retrieves and loads the data from memory. When the processor encounters the speculative check instruction, it verifies the load before allowing the program to use the loaded data in the next instruction. If the load is invalid, the processor does not immediately report an exception. It postpones exception reporting until it encounters a check instruction that matches the speculative load. If the load is valid, the system behaves as if the exception never happened. Speculation techniques combined with prediction techniques give the compiler more flexibility to reorder instruction and increase parallelism. From this, it is clear that all three techniques are based on the availability of an intelligent compiler and close coupling between compiler and processor. Hence, performance of processor based on EPIC technology, that is EPIC technology, comes from both hardware and software. Processors based on EPIC architecture are simpler and more powerful than traditional CISC and RISC processor. These processors are mainly for 64 bits high-end server and workstation market, not for personal computer market. For example, Intel's IA64, code named Itanium, was the first EPIC processor.